Any questions regarding the homework? Regarding the certificate, we are nearly to issue the medium level certificate. This will be the last week while we're waiting the results on the contest. Then we will issue them. So, and we are on the second week of hard level week. Means today we will cover tries, and next 2 weeks we will focusing on graphs. So if there is no questions, I will go straight forward to lecture. It should be, let's see how it will go. There is not that many materials which needs to be learned, and we will cover 2 questions. I'm sharing my screen. And I think we need Irina, or we already have recording. Because been recorded. I believe we started recording. Okay, let's get started. So last 2 weeks we were covering 3. Today we are going to cover tries. Is anyone familiar with tries data structure? Just raise your hand if you ever heard about this data structure before. Okay, so tries. Tries, it's another type of tree, which is usually called as a prefix tree. Means it's literally just prefix tree, which will contain only letters. So to understand how try is working, let's look at the example. So imagine we have words, which is internet, and we are building the tree with this word. It will look like this. But let's imagine that now we want to add to this tree the word interface. Instead of creating a separate sequence of nodes, we will reusing of the common prefix inter, and both words can share the nodes of inter, and the remainder of the interface can branch out from the R. So first, with the one word internet, our tree will look like this. Once we will add interface, we will reuse all common prefixes, and then we will branching these words. This is the whole idea of try data structure or prefix tree. Yeah, this is essential to understand what is this and why we have this. It's basically for sharing prefixes along the different words. Nothing much. Okay, is this understandable? Yeah. It is in the chat. I will just repost it again. Okay. So now, as we discussed before, how tree node looks, how linked list node looks. The same apply here. In order to implement a try data structure, we need to have try node. Try node is this one. So, for example, this one is try node. This one is try node. It will look like this implementation. So each try node will have a reference to their children's, because it is not the tree which we discussed last week, where it was at most just one child. Do you remember, folks? There was left and right child. In this case, there could be many children's. It could look like this. As many branches it will have, so that's why when you're developing try not, you're including the map of the children's, where it is contain the character, and try not on the another node. And also we have is end Boolean flag to identify if the word is finished or it is still prefix one. So yeah, if we look at this tree, we can see how it will looks like. We usually starting from root identified. Root doesn't have anything like values or something. It's just root, simple one. You will see how we will create it later. And then we're starting entering our words to this tree. So we first, for example, we have this list of the words, and that's how we are going to build our tree. We will enter first, for example, internet. It will be go like this. Then there will be another word, interface. We will look for each character which is already present. Once we find out that there is no any common prefix, we will branch it and we will start another one. Once we will finish with entering the whole world, we will identify that the word is actually finished. So at any branch, we will have at the end of any words, we will have is the word true. It could be like this. So for example, here we have word byte and we have world bytes. It will go the same way. We will enter first, we can enter bytes actually here. And then we can enter byte, and we will find that the common prefix actually share it, and there is no branches. We're just putting is a flag, which is pointed that this is the whole world. That is not the prefix. So there is doc and dic. We start, yeah. So this is how the try will looks like, how it is generally looks. And today we will cover how to build this try, how to insert words, and how to search prefix, how to search the whole world. This is the common problem usually covered. There is not many LeetCode task which is use try. Usually it is usually it is to build try, and with some tweak how to find prefix with wildcard, or it could be some task which is you actually can solve without try prefix, without try tree, but with string capabilities. And it is okay during the interview to say, so for example, when you need to find common prefix, you can try to solve it just with string and all the methods which is available for string, or just to iterate to find the common prefix. And then you can mention that, oh, okay, there is like shared prefix, probably we can even solve it with try, and you can just acknowledge that you know this data structure. And most likely it will be enough just to solve with the string. But if there is task which is required, you implement try or implement search by prefix or something. So it's definitely will require it to implement this data structure. Yeah. And so basically all the LeetCode task will be around how you implement this data structure. It's not that you will use it out of box and solve like it was with heap. But yeah, you would need to build and just implement methods like insert, search prefix. We will cover all of them. So when to use tries? Yes, if the interview problem asks to find string that share common prefix, it's 100% of try. But don't jump quickly to solve it with try, because this is considerable to be advanced algorithm task. And sometimes it's enough to say that I know this data structure, but let's solve it just with string capabilities. Yeah, and this is just why they optimize data structure by reducing redundancy through shared prefix among string. Tries are also useful for word validation. This is the real use case. Okay, any questions? Because now I'm going to jump to our first task, which is calling design a try. Yeah, please ask.
Good morning, Livia. I just have a quick question about that kind of tree itself. So if you move it to the picture in the beginning, so when we spoke about internet word, for example, if we want to add word networking to the try, would it start from the root or it would start from net bit because it already exists?
Yeah, no, it will start, it's a good question. It will start from root. Because you will start from root and then first will be this one. Yes, this is a good question. No, we are not going to proceed from here. It will be always go from root. Means you will check the first element I, and it is not here, and you will build the network here.
Thank you.
Yeah, very good question. Thanks. So, done?
Sorry, Lydia, can you just go to that tree below where you showed bytes and other words? So here, okay, so what does the root node represent in terms of
Root, it will be, it will be empty one. Yeah,
okay.
like this. It is always empty.
Right.
It will start from just empty root.
Okay. Thank you.
No. Yeah. Yes, Ellie, please.
Hi, sorry. I have a question about the last point, how to use tries. About they help optimize data storage. Do you mind to explain that again?
Optimize data storage because the characteristic which is we use for try, instead of inserting here two words like byte and bytes, we will insert just one, and we will reuse all the prefixes which is available. This is that's why it's saying that it is optimized data storage.
Thank you.
Mm-hmm. It's widely used in the search, where you need autocomplete or you're just searching in Google. So basically, all of them building try, and there is a little bit more like with all. So for example, after complete how it is work, you're entering B, and with B there will be associated list of the words which is could potentially be after completed, and then Google will suggest you that you can use this one. So for example, yeah, it's widely used in search. Okay. So design try. Design and implement try data structure that support the following operations. This is the what needs to be done. It's how it will sounds. Design and implement a try data structure that support the following operation: insert, search, and has prefix. When you're inserting, you're not returning anything. Search, you return boolean if word is exist in the try and false if not. And had prefix boolean return if the I don't know what is written here. Train word with the given prefix and false if not. So basically, it will try does not contain the words to return false. Yeah, try has top, by, and to. So insert try contains the word to, return true. Yeah, with prefix it will be also return true, and with word it should also return true. From the description, is it clear what needs to be done? So we need to implement data structure which is supporting three methods: insert, search, and has prefix. And tries most of the tasks on the try LeetCode interview questions will look like this. Yeah, and there is explanation. The same way we will define try not using the same definition introduced in introduction. In this implementation, this word attribute will use to indicate whether a try not marks the end world. So implementation always will stay the same. It will be a class try not map which contain a character, and next it will be a child. Boolean is end world and try not. So in how we usually initialize try not? Word insert into try will branch out from the root node. As I mentioned, it will be looks just like this, and it will doesn't contain anything at this point. It will be empty. It will be just root. Is it clear? We're defining try not always. Then in the try class, we will initialize our actually try. There is I can show here. So this is class try. Usually I'm doing embedded class in the try, which is described, and then this is the class. It could be out or inside of class, and then you just initialize it. Yeah.
Could you please give an example of what the hash map contains for each node?
Yes. So hash map will looks let me see how to explain how in this case we will have hash map, which will be a character. So for example, here the root will be as we have our constructor, it will be new hash map. Root is not false. This will be root will looks like this. Character will be empty, but it will has associated list of the child. And if we look at this, so for example, at this example, how root will looks like. This is our root with empty character because it doesn't have any character, but root children in this case will looks like T and B. Next, so for example, when we come to T, it will be our T. It will be our character here. And next, this character also will have a children map, which will contain just O. And these children are also associated. There is all T, for example. It will be also has a hash map of his kids, and B also will contain hash map of the kids. And here we will have also like associated hash map of the kids. Is it clear?
Yes, thank you.
Yeah. So each kids will have their own list of children and character, just their character. Once we will go to search and prefix, I think it will be more clear. So yeah, now let's go to inserting a word into try. I will explain just how we inserting, and then I will show code. So the insert function build a try word by word. what makes a try useful is that, again, we use redundancy by reusing existing nodes when possible. What does it mean? I will already explain it. You will have a list of the words. You will start building tree word by word. You never go with a whole list. You will take the first word and you will insert it into try node, starting from root. Root will always be empty. We will take top, for example, byte, when bios already exist. Yeah, let's go by lecture. So already exists in the try. There is two words should share the node that makes prefix byte to save. Okay, just, yeah, start from root. You will go with top first. So for example, this one doesn't exist here. We don't have this one. If we will start from top, we will insert each character by character. First two, then O, then P. Once we will done with top, we will know how we will done with top. It will be used. So for example, we have this insert function. It's taking words as a parameter. One second, where I'm calling it actually. Okay. So yeah, because yeah, there is won't be list because we're implementing just insert function. You will give at the beginning just top. You will call the function and you you're going to build this word first. So initialize root. You always will start from root. Any words which is coming, which is you need to insert, will start from root. This is the questions which we just covered. Then you're inserting character by character. You always check if the character is already exist in the try data structure. If it doesn't, then you're putting it. If it exists, then you're moving. How you're moving in the tree? You're taking children, you're taking get A, and then you're moving to not. That's how it works. Next, yeah. So basically, once you finish with entering tries, you're with the entering words, you are just identify whether the word is finished, and if it's finished or not, you are putting true. By default, it will be all these elements false. So we can walk through the diagrams now. Yeah, we will start from root. Any words start entering from root. So for example, by is already exist in the tree. You're traversing around, going B, Y, and E. Next, Y is still a child of the current node, but then you're admit that T is not actually exist here. It's not a child of the current node. Then we are doing what? We are creating a new node, a new try node, and we are associated with Y. And once we finish the traversing, we are saying, is word true? It exists. And then for byte, we entering Y, E, and it is will be the same. You just extending T. You're creating new node, and yeah. So let's create node bytes at as where is the word true? Yeah. Is it clear? I believe it should be clear, at least from the code. There is not that. Yeah, it should be understandable. If it's clear, I will move to the searching word now. Okay, cool. Searching. Searching for word involves the same strategy as in the insertion, where we move node by node down the tree. So we will move the same way like we're doing with inserting. If node corresponding to the current character in the word isn't found at any point, we return false, because this would indicate the word exists in the try. After traversing all characters of the search term, we return true only if the final node is the word attribute is true. So what does mean? We are searching for two, for example. We have this try at this already built, and now we're searching for two. If we're searching for two, it's apparently we don't have world 2 here. We have word 2, but not 2. In this case, once we will search down the tree, we will return false. Is it clear why we are returning 2 and top? Okay. Let's look at the code. Search prefix and search will share the same logic. We will start from root the same way like we are starting from inserting. There will be parameter on the input, which is word. We start from root. We are splitting the word on character, and we will look character by character. So if we didn't find the character for the road, we right away will return false or null in this case. If we will find it, then we will just traverse the same way like we're traversing. We are taking children, we get the character, because this is also clear, right? Because at the beginning I explained it, that node can contain different children's with different character. That's why we are taking the list of the children, and we're taking exactly by key, by character, the child. We are assign pointers to new node, and now we are going to the next iteration with the new node, and we're checking if the characters exist or not. So yeah, as you see, they will share a lot between insert. It's very nice to remember how the try is built, because they share it common logic. You're starting from root, and how you travel across the nodes, it will be logic which is shared between search and insert. And the one difference is that when you're inserting, if there is no character, you're actually creating new node, new try node. And when you're searching, means you didn't find. So this is the whole difference. With the prefix, as a search prefix, and a search itself is reusing the same logic. The one difference here will be, once you receive this node from the search prefix, you will check if it's null, because we're returning null here. You can introduce any logic, you can return false. And if it's not null, we actually find the node, we are checking if it's this actual world in the tree, or it's just someone prefix. With prefix, you are just omitting this part, because you don't care whether it's world or a complete or incomplete word. And that's why, you're just returning if it's not null, and returning your answer. Is it clear? Okay, just to cover, it sounds, for me, it's a try was always sounds very advanced data structure, but actually it is very easy to remember. So everything what you need to remember, the structure of try node, that it is including hash map children, where the key is character, because when we will have list of nodes, we need to find the exact node of the try. Boolean, it is we usually have this flag as an indicator, whether it is the end of word or it is just the prefix of the word. Initially, how we initialize try, it's always like this, so it's empty. Root doesn't contain any elements. We're starting from empty root. And all insert and search will start from root, and then from the root you're starting to build. Need hash map. I will answer this question once I will finish. Yeah, you always starting from root. The same traverse logic between search and insert. And yeah, so basically that's all what you need to remember about how to implement try data structure. On the questions, need hash map or not? This is also a good question. It's you can always use hash map, but there is some tweak exist. So for example, if in task there will be told that it is just small characters, English small characters, we right away know that we can use static array of 26 characters. And there is will be like a small optimization. Instead of using hash map, you will use just array here. I will then I can share on the Slack some implementation. Yeah, please, questions.
Yeah. So we are using hash map to maintain the child of that character, right? So in
Yes.
case of so how would this work if we don't have a hash map?
It won't work. You should maintain. You should maintain links to your children's. The one optimization which, as I mentioned, you can use array if you right away upfront knows that there is will be just, for example, some set of characters. Like I mentioned before, it will. So, for example, upfront, you know, there is will be a set of low case English latest, which is 26. Then you can make optimization array, but it is just optimization. You can always skip it.
Okay.
But you always need to track your children's. It is the tree data structure. What we discussed 2 weeks before. I mean 1 week ago. But during those 2 weeks during the implementation during the 3-part 1 and 2, we discussed that there is could be at most 2 children's. It is left and right. That's how we were defining. But there is different type of tree, and it is not obligatorily being a prefix tree. There is different tree which is also included a set of children's, not limited by 2. Then you need to introduce data structure which will actually track your set of children's. This is how it is always will work. You have not. And you have association, you need to track it.
Got you.
In this case, also why we're having hash map, because we need character to identify which node actually we're having. Like for example, here Y can have E and T. In order to find the T, if Y has T character, you need to call a hash map by T and just return the actual try node of this one. If it's good, then we will move to another one. Task which is with slightly tweak. Oh, good. I'm moving, folks. Okay. Now, approximately the same, we need to implement, design and implement data structure that support the following operation. Insert, the same way, and search. Return true if word exists in data structure and false if not. The word may contain wildcards. This will be our wildcard that can represent any letter. In this case, how it looks. You insert, for example, bat, rat, and now your tree is contain these two words. You are searching for ra, and for any for any words which is including prefix ra, and dot will represent the wildcard. Means there could be any elements, and you need to return if it's if we indeed in our try data structure have this any words which will map to this pattern. So it could be two dots here, but as we have three latest words starting with B, there is no, we have only 4, we will return false in this case. But if there will be 3 dots and B, we will return true. We should support the same way run. So for example, insert, we should support also full search when all the characters is, we have. Also, we should return true or false. And the wildcards can come from beginning. It could be in the middle. It could be at the end. Is it clear? Okay. The requirements of this data structure closely go with try. Prefix required support wildcard and search. Let's learn how we would need to modify our try function to support wildcard. From the inserting perspective, there won't be any change at all, because we will insert words as it is. On the insert points, we are not inserting words with wildcard. It's only for search. Insert function will stay the same as we implemented it before. Here, the code. So we will have again our try node the same way. Hash map, character try children, and hash map. There is constraints of 26. We potentially could use array. But yeah, I will share later because I don't exactly remember how I was implementing it. And it will be slightly different implementation for insert and search. But it is just implementation, folks. It's not something which is you obligatorily to use during the interview. But just for sake of knowledge, I will share on the Slack. So same, we have our class. We have our embedded class. Which is try node, and then we are initializing our root. This our insert function. It's absolutely the same like it was before. There is nothing new. Now let's discuss what needs to be done in order to implement the search which support wildcard. So let's look at this tree and let's try to search array with wildcard. If we perform a search for array, we know we can traverse down node R and A until we reach the wildcard character. Since the last letter is wildcard, it could represent any letter. So as long as there is existing node branching out from A, that represent the end of the world. For example, any means both of them will actually suit our search. In this case, yeah, both T and N meet the requirements of the wildcard. And everything what we need to tell, so we will search as we have RA at the beginning. We will start from root. We will find that in our try indeed we have R later. Then indeed we have A later. then we find the wildcard. Now we know that a character actually has two children with different elements. Everything what we need to know from this, if it is indeed the end of the world, and there is no other. Otherwise, it won't be meet our requirements. But in this case, both of them, this child nodes is actually the last one, and we can return like right away true. Don't know, even like we will check that rat is meet our requirements, and we don't need to check if n is also meet our requirements. It's enough just to return true. At least we have one of the word which is meet requirements. Is it clear? Okay. Now let's look at another example, which is required as a search from wildcard, which is including at the beginning. Now, let's say we perform search. Since the first character is wildcard, we need to cover all branches, starting from every node representing the first character in the try. This is our root node, and means we need to start from all branches. If there will be 5-6 branches, we will consider all 5-6 branches, because this wildcard from the beginning means we need to go and cover all the branches. This means starting a search from each child node of the root. We can do this by recursively calling the search function. Here we will, this is a tweak which required a recursion function used, as we cover in the part 1 of the tree. I will do a dry run with the recursion function in order to make it more clear. So how we will recursively calling the search function on this node? We will passing a substring after all n, because this substring contains the remaining character to be searched. Means we will start from root, and next we will recursively call our search function. But we will call this recursion function with substring, which is in. If there will be more dots from the beginning, we will do this recursive call until we will have the proper substring to search the try nodes. So, for example, as this B and R will actually work for us because it's dots, and any of this character can accumulate, can meet our requirements. Next, we will go to next try node, but we will scan this substring. So we will check if A is present, if N is present. It's indeed in this branch it is present. And here, R is meet our requirements because it's wildcard. And indeed, we have A. But one branch is not meeting our requirements. We need N. So basically, we will find words in both branches. But this branch will not meet our requirements because here is not enter word, and it will return false. Means we need to explore this branch. And in this branch, we have 2 more branches to explore. T won't meet our requirements because we're looking for N. Here will be false, and here we will call, we will go to the N, and we eventually will find that we indeed have a word which is meeting this pattern. Is it clear? I will cover now in the code how it will looks like.
So one quick question I have here is, so it doesn't matter how many ever nodes come before A, right? But once we hit A, we have to check its children is, one of its child has.
Yes, and in this level, yeah, we will start as root. We're just starting from root. First character will suit any, means it could be B, it could be R, it could be, if there will be more branches, which is starting from different letters,
Yeah.
we will all consider them. Yeah. Once
But
we,
if let's say there was one more level before A was there, like after B, let's say there was a word, there was a letter like S, then we have the letter A. That's not correct, isn't it? Because it's that wildcard is only for one character.
yes, yes, yes. If there will be C, for example, we are not considering this branch. We will consider only this branch.
I mean, not a branch. I mean to say, if the word is, say, BLACK, so how would you do that?
Can you
Uh,
put on the chat?
Okay, 1 second. Check.
Without wildcard.
No, what I'm saying is, let's say the word is blank. So
Blank like this?
yeah, BLANCK. No, not that's not the wildcard. The wildcard is still .an. But while searching through the tree, try.
In the tree we have blank. Gotcha.
Yeah.
Yeah, and this word won't consider because we have wildcard which is associated only with one letter.
Okay.
So there will be B. But next will be L, and it won't work for us.
Okay. Yeah.
Mm-hmm.
Thank you.
So forming the string one will not satisfy. So at any point we search, we need to handle two scenarios. When we encounter a letter, we proceed to the child of the current node that correspond with the letter and try. So yeah, this is just two scenarios. As I mentioned, there could be just character by character, and it will fit to the one implementation which is we just discussed before. We will just walk through all the child characters and we'll try to find if it's matching. And the second, we encounter a wildcard. We explore all child's nodes at the as if we will have dots, means everything is will accountable on this level. Or for example, if we meet somewhere here, this will be also accountable towards the wildcard. Allow us to search every possible branch for node matches. As soon as we find branch that represent the word matching, the search term will return true. So this is the method implementation of the search, how it looks like. Let's walk through of this. We make a little bit tweak to the search function here. So basically, there will be search function. We are saying from the beginning that it is we need to search for it, and from the beginning, our try node will be root. Next, we will calling the helper function, which is actually our recursive function. We will call it here. So we're taking word. There is nothing changed. We again working with character by character. At the beginning, we are checking if this character is exist and try indeed, or it doesn't. If it's exists, we just going and traverse the same way like it was before. We are saying like, okay, we are the level B, and B has children A. So for example, and we are looking for the word which is bank, and we indeed has our prefix like B. So means here it will take B. It will check if we have this node we have, we will move to A. We will move to A, to the node, and We will go to the next iteration. Yes, we will have A. Yeah, and here we have already a node which is actually A, and from A, if there is like n, we will check if the n is indeed as a part of this word. If it's indeed, then we are going to call this branch. But there is things. So, for example, we are not encountering n here. And so, for example, we are saying here it will be k, but we don't have bug in our try. What will happen here? We will check if it's not exist. We will go inside. Next, we will check if it's wildcard, but it is not. Then we just return right away false. This is the basic cases which is we cover. Now let's go if instead of k, we will have here dots. For now, it is clear how the search will work. Should be the same like it was before. Nothing much. Now let's cover once we meet the wildcard. So we're taking all the kids here, as I described. We're taking the whole level, other here, other here. What we do next, can I ask who is this pointer impassable shell? Can you move, Fox, from the code from here? Or let me move over here. Okay, so once we encounter a wildcard as a dot, we will take all the kids from this level of the node, which is, of the node. It will be our A. And now we have all the nodes. Node by node, here we will return children. We will take first character, and we will call recursively our search. And we will substring here. So for example, if we had world like bank, for example, and the rest was wildcard, what will happen here? We will actually call the recursive function with the substring nk and with new node over there. Will be with the new node. Yeah. If we need to continue, and it will be our next. 1 second. So the rest will be if we are going A. After A, we encounter our dots here, and next we will take children's from A. Not doesn't will be B. If it's not exist, we have A. Okay, and from the not children case set, we will have A, and we will go to the next node. Yeah. So and here will be we will take from A our characters, which was T and what it was. It was T and N. Here, not children case set. BA. Next, we will go with this one. Not children doesn't contain. Okay, we will check if it's wildcard. We will return this TN. And now from TN, not children get X. And here we will skip this level. We will ask if T, so for example, has another node. That's how we are skipping the levels. So, for example, we are starting from here. Next, we will encounter the case where it is wildcard. We will take from root all the childrens, but we are not caring about them. We are caring what they have behind. So we're basically switching right away to this list of childrens where we are asking them, can you return me the next try node of this level? Once they will return our next node level, we will send, actually, there is a substring, which just needs to be looks for them. We will go with nk, and we will go from the next try node, which is we obtain from the level which is we are going to skip. And in recursion function, so we will enter, we will go again one by one. Once we will find or we traverse the whole world, we will return the answer over there. Is it clear? Also, I posted here dry run. How it will work. So we can walk through them. We will start from root, start R, children. This is the basic case A. Then we having wildcard. Not a literal K because it's we try all the children off. Try with remaining word substring. Loop ends immediate. Not is end at T. And since one branch return true, the whole search true. Next, we will go with N. So at this point, we will start at root. Try every child of the root with remaining words N. Branch B, call search and not. Child of B is A and N. This one. Once I will just will enter the one second. I will enter the example of the tree which I'm traversing actually here. Children of A from here and here. A go to N, a child of N, go to N. Yeah. So that is the tree for the dry run example, which I'm using. Exist, wildcard, try children, A again, try children. So yeah, folks, if you have any questions, I can try to answer. What is, it's very silent. If it's not clear, I can do dry run on the examples. But in general, there is, the trick with recursion that you just need to go with substring and next node. Just to remember that you are not exploring the node on which you're actually skipping because it's fit the wildcard. That's why you need to call next child node of the level which is you are skipping. and you just calling the recursive function with the new node from where you are proceeding the search and with the new substring. And as many wildcards you will meet, then many recursion call you would need to call. Any questions? Okay. If none, so basically I made just 2 tasks this time. This is all on the try. We will have as our homework implement try and design, add, and search for data structure with wildcard. So nothing crazy here, and I believe it should be now kind of straightforward for you folks. Intentionally, I decided to not overload with others try tasks because they most of them required recursion or backward compatibilities knowledge, not backward compatibilities, but backward some dynamic programming knowledge. So that's why I decided to go just with try implementation and with wildcard. And also do not expect that there is many questions on the LeetCode exist for this data structure. But anyway, it's something which is we need to know. Okay. Then we can finish today a little bit earlier, 1 hour earlier. And next session we will start from graph. Kind of problem. Thank you, folks. Thank you.
Thank you.
Thank you.
Sorry, can I ask a question?
Sure.
Is there a specific channel in Slack for this group? Because I found the summer bootcamp one, but it's quiet there.
Yeah.
Okay.
No, it is not the one.
Oh, which one is it?
1 second, I will share with you.
Thank you.
It's this one.
Thanks so much. Is that in the Slack?
Yes.
Okay, cool. Thanks so much. Thank you for today.
Yeah. Thank you.
Bye.
Bye. Thank you, folks. Bye. Have a good weekend, everyone.
Bye. Have a good weekend.
You too. So.